I noticed that my mic was off. Now it's on. Okay, so homework. You had two types of homework. The first one was just finding the Jacobian. So let's look at that. Make sure that we're okay with those. That you remember sort of the pattern. It's not too difficult. When you do a few of them, it's pretty easy to see how it fits in. But does anyone have any questions about that, the Jacobian? So you can do it pretty easily. I mean, one way that I think of it, and all I care about is that I'm going to write down these derivatives. So here, I'll just pick one of them. Let's just pull this one out, just to remind, just to have a quick reminder. Then we'll move on to the second set, which was a little harder. So with this one, for example, I'm going to do derivatives for x. So I do the derivative with respect to u. And then I do the derivative with respect to v. So that will be just u. So this is going to be x goes here. This is the derivative with respect to u. This is the derivative with respect to v. And I make a little grid, a little table. Then I do the same thing for y, derivative with respect to u, derivative with respect to v. And then once I have that, then I can just do this trick, doing the matrix determinant, which is a 2x2 matrix, but it's the same pattern that we learned. So you have 2u plus v times 2v, try 2uv, sorry, that's where it is, and then subtract off, I need to make more room, oh, well, I'll leave that there. And then you subtract off the upper diagonal, which is u times v squared. So it'll be this thing minus this thing, and then clean things up. And I think something, yeah, you can combine some like terms after you get done doing that. So multiply, and then you do this minus the upper diagonal. And you're all done. So at least that's the way I always think of it. And as long as you're consistent, you could switch the x and the y. You could switch the u and the v. I don't care how it works out. You're still going to get the same. You'll get the same thing with up to absolute value. So make it all positive, and you'll be fine. Okay, so let's move on. Hopefully you didn't have any trouble with those. Moving on to the second batch, which was this. We had started number 15, but we can look at any of these if we need to. And the hard thing here, I think, the hard thing here is sorting out the difference between what you're given for your transformation and basically what is u and what is v. So in each case, you're going to have to take these, whoops, not that, there it is, these, and you're going to have to rewrite them so that u is equal to some function of x and y, and v is equal to some function of x and y. And that's just so that you can actually do the transformation. Anyway, at least I find it useful. I don't know that there's a better way to deal with those. That's the issue, is how to, you've got this region with these corners, and we did this earlier. Where is it? There it is. Yeah, there it is. So we already did it, but you need to know, like, where did these end up? This is x and y. Where did those end up over here? So you end up solving the equations for u and v. And so that's what I find to be the most labor intensive. The rest of it, Jacobian's easy to find and so on. But we can look at one of these if we need to, or maybe more than one. So was there any of these that caused particular sorrow? Oh, yeah. What do you think, Austin?
The last one.
Which one is that, 19? Is that right?
Yeah.
Okay. Just want to make sure I got the right one in mind, because I don't have the actual homework written down here. Yeah, let's take a peek at 19, see how that works. I'll put it down here where I have more room. Okay, so there it is. Let's do this. Sorry. Pull it down below the line. There we go. Okay, so here's 19. So the way I would do this, the way I would start this is, first of all, figure out what, well, I guess you can do the Jacobian, but the main issue is, what is this going to look like? So this is similar to the one that we did in class. We have these two hyperbolae. So y, here we are, this is y is equal to 1 over x. And then this hyperbola, I'm exaggerating the difference between them so I can have room to write 3 over x. There are these curves. Then you have these. This is similar to what we did in class. This is y equals 3x, and here's y equals x. So the region that we're interested in is this. So you can see it's almost the same as what we did, very similar. But you're given these as your transformation. You're like, well, let's try these, or this is what they're suggesting. So let's see, for this, for this one, I guess, so this is x and y. Maybe I don't need to solve for here, let's see, u and v. Let's see if I can do this without having to rewrite this transformation. And what I mean by that is, normally I always like to figure out u as a function of x and y and v as a function of x and y, but I think I might be able to avoid it in this case. So let's see if we can. So what I would do is I would take those two and plug them into each of these 4 functions that we've written down. So for example, y is equal to x. I'll do that one first because that one seems to be the easiest. If you take that and transform it using what's up there in circled, you get v is equal to u over v, which means that u is equal to v squared. That doesn't feel as nice to me as what I did last time, but that's all right. We'll work with it. So u is equal to v squared. So that's going to be this parabola. Whoops, not v. U is equal to v squared. It curves down here as well. I'm not sure how much of this we're going to need, but that's going to be the yellow. So I'll highlight each of these. That's that piece. Okay, let's see what happens with this one. So doing the same thing, I have y is equal to 3x. So v is 3 times u over v. And that gives me u is equal to 1/3 v squared. Might have been more convenient if I had written this over here with u pointing up and down. I always think of u as going left and right though, so I'm stuck. Okay, so u is equal to 1/3 v squared. That parabola is going to look something like this. It's shorter and squatter, so that's going to be u is 1/3 v squared. Let me highlight that. That's this one and this one. Okay, so what this transformation has done so far is it seems like it's not helping me out. So that's why I'm a little skeptical of this particular transformation, but let's keep going. What it's done is it's taken these nice straight lines and turned them into parabolae. Why? Well, maybe it'll become more obvious once we get to this next bit. Okay, so the next bit are these 2 hyperbolae, and I'm going to use the way that they're written up there. So let's see, we'll get another highlighter. Let's use the blue. So we'll do y equals 1 over x, which is the same as xy equals 1. Here, just a minute. Let's see, this one was the yellow thing up there. Okay, y is 1 over x, xy equals 1. So let's put this down here. Xy equals 1. And let's do the same transformation. X is u over v, and y is v. So, well, that worked out nicely. U is equal to 1. U equals 1. I'm still not happy about this, but okay, let's just put it right here. Put a 1 there. It's U equals 1. That was the blue highlighter. There's the blue highlighter. Blue highlighter. Okay. Am I doing all right? Last one. Last one is this. So here, I'll highlight with brown. Does that show up? Sure. So that's this one. So let's crank that through. Xy equals 3. So u over v times v is equal to 3. I'm really not happy about, well, it's okay. This is, there's something bothersome about this. Like, why? Why would we make it like this? It's okay. And then this is u equals 3, not to scale. There. Okay, so far so good. I've done all my algebra correctly, haven't I? There's nothing, u is, other than my annoyance at this particular transformation, there's nothing other that's wrong. Okay, so here's a thing that bothers me, is are we talking about this up here or this down there?
It says first quadrant.
Yeah, first quadrant in X and Y. But where does the first quadrant go when we transform it? Does it go down there or up there? So we have to actually do a little bit more work just to be sure. So I guess we could pick a point, like this point right here, point 1, 1. Where does that go? Does it go down there or up there? So if X is 1, Y is 1, 1, 1, those will be positive as well, won't they? Because V is equal to 1, U is equal to 1. So that goes to this point. So it's that one. Yeah, so I guess it's still annoying to me. So let's see, we're talking about that upper pink blob. Now we can set this up. Let's go ahead and do this. We're nearly done, believe it or not. So we're going to do a double integral. The u is easy. U is going to go from 1 to 3. The v is going to start at the square root of u and end at the square root of 3u. All I've done is I've solved those two equations for v, and that's where my limits came from. I need to put my Jacobian in here, and then I'll multiply that by what I get when I transform that x times y into u and v. So u over v is x, y is v. So let's just grab our Jacobian, and then we'll be all done. So the Jacobian, let's see, I'll just draw it like this, because this is the way I like to think of it. So derivative of x with respect to u is 1 over v. The derivative of x with respect to v is negative u over v squared. The derivative of y with respect to u is 0. Derivative of y with respect to v is 1. Well, that's convenient, because when I do that Jacobian, I only have to worry about this, whoops, this down diagonal, and the up diagonal is 0. So if you did it using the formula, you would get the same thing. Derivative of x with respect to u times the derivative of y with respect to v minus the derivative of x with respect to v times derivative of y with respect to u. So there it is. There's my Jacobian. So what do we get? Oh, well, that kind of makes it. Is this right? Sorry, now I'm doubting myself, because this does not look like it's going to work out nicely. We're stuck with it. We're going to do it. Okay, so u equals 1 to u equals 3 of the integral from v equals square root of u to v equals square root of 3u times u over v. Because when I multiply all these three things together, it's just u over v, right? All right, I just want to make sure, because this is not making me happy. Not at all. Why did they do this to us? Well, I would have done a different Jacobian, different transformation. Okay, dv, du. Okay, let's finish. This is going to be natural log of v, y times u. Okay. U equals 1 to u equals 3. Natural log square root of u times u. Oh, sorry, 3u. upper limit first. That's no good.
Can you not just use log rules and consult?
Yes, you can, but I just don't like it. So this is going to be 1/2 natural log of 3u times u minus 1/2 natural log of u times u. Okay, we'll use the log rules. Still 1/2 natural log of 3 plus 1/2 natural log of u times u minus 1/2 natural log of u. Okay, it's redeemed itself. Okay, it was a good thing I did. Thank you. Thank you, Emily. Because, yes, the thing that was really bothering me is going away. There, phew. Yeah, because that cancels with this. Okay, now I'm happy again. I don't have to be angry. Okay, so it's still the natural log of 3, whatever, but it's ugly. But we're doing, now the rest of this is simple. You've got 1/4 natural log of 3 times u squared evaluated from 1 to 3. And that's going to be 2 natural log of 3 in the end, because that's going to be 9 minus 1 is 8. So is that the right answer? Is it back in the book? Whew. Okay. Sorry, I was getting irritated up here, as you can tell. But yeah, it worked out in the end. Oh, I'm happy again. So yeah, I would not have used this transformation. Honestly, that the reason being that there's another transformation that would allow you to have this be here. I'll show you what I would have done. This is neither here nor there because it didn't tell us. It said use this one. So I would have done this. I would have had x. Let me make sure I get this right. Yeah. Well, I would have done it this way, I guess. I would do u is equal to like x over y, and v is equal to x times y. And the reason I would have done that is because it would straighten out all 4 of these. So here, divide both sides, y over x, not x over y. Divide both sides by x, and you get y over x for the parabolae, or no, the hyperbolae. Oh no, I'm sorry, these are the straight lines, become y over x, so this is u equals 3, u equals 1. This becomes x times y, well, it's right there. That's v equals 1, v equals 3. So I would have done that, because then I'd have nice straight lines. You get the same answer, I'm sure. It's just, why do it the hard way? But apparently they like it the hard way. Yeah, it made me worried, to be honest, when I saw this natural log of the square root. Whew. Well, in the end, it worked out. Any other questions, concerns, fears, worries? We can move on? No, we can't. What do you got? 16? Okay, let's take a look. Let me see what 16 was talking about. We won't do the whole thing like we just did because there's too much risk that I'll get it wrong. But let's just get it set up to make sure that you know how to do this. So the big deal with number 16 is coming up with your region, because the region is a parallelogram. So what I would suggest you do, I think what I would do is, instead of figuring out u and v for each of these, so these are all x and y, and so instead of doing that and transforming each one of them individually, probably it will be easier to take these together and solve for u and v. What I mean by that is you'll take this, I get x is equal to 1/4 u, no, let's just multiply, sorry. So 4x is equal to u plus v, and then 4y is equal to negative 3u plus v. And then subtract one from the other so that I get 4x minus 4y is equal to 4u, and u is equal to x minus y, and then you can plug that back into one of these. Let's see, I'll plug it into the first one. 4x is equal to x minus y plus v, so v must equal 3x plus y. So there is my transformation, and that allows me to transform each one of those. So for example, so I'm not going to do the whole thing, but for example, the negative 1, 3, when I plug it in here, u is equal to negative 1 minus 3, which is negative 4, and v is equal to 3 times negative 1 plus, well, that's going to be 0. So in the UV plane, you have negative 4, I guess that's back here, and 0. That's this point right here. So that point corresponds with this point, negative 4, 0. You could do the same thing with the others. Let's see, I can do the next one is pretty easy because the next one is just the negative of the first one. So that one I think is just going to be right here at 0, positive 4. So that's going to be the second one. Highlight this in blue. Ends up being right there. I should label this. And this is U, this is V, this is negative 4, this is positive 4. I guess since I've already done this one, I might as well do that one. 3 and negative 1. When x is 3, y is negative 1, plug those into here. And you get U is equal to 4, and V is equal to 3 times 3 minus 1, which is 8. So that's up here. That's 4, 8. And I'm guessing that the other one is going to become negative 4, 8. I better double check though. Where to go? 1, 5. When x is 1 and y is 5, yes, u is negative 4 and v is 8. So you end up with this nice rectangular region. So when you set up this double integral, you'll have the limits. U will be from negative 4 to 4. V will be from 0 to 8. Throw in the Jacobian. The Jacobian is going to come from those transformations. I guess it'll be 1/4, 1/4, negative 3/4, and 1/4. Let me just think. 16th minus 3/16 plus 3/16, 1/4. Is that what we got? Jacobian is 1/4? Maybe? Whatever. If it is. Anyway, so you throw in the Jacobian, make these replacements here, and then you'll have a nice, beautiful double integral. So I don't know what the final answer is, but this is the hard work, I feel, is figuring out what the new region looks like. Because those 4 points, they end up being this orientation, beautiful rectangle. Rectangles make us all happy, don't they? They do me. All right, well, you know what I did? I printed up a quiz for you. It's sitting on my desk right now, I'm sure, because it's not sitting in my backpack where it belongs. Let me double check. Which makes me sad. Sad. Not there. Just a minute. There's still hope. No. One more place. No. So, sadly, we don't have a quiz. Well, I mean, I've got this we can do. It's not that exciting to do it on a piece of paper, but there's 2 problems. The second one takes longer, so let's just do the first one just for practice. See if you remember your Jacobian. See if you can do it without looking at anything or anyone else, and we'll go over it so we don't get to do this as a group today, or we'll do it as a group. I have extra paper, scrap paper if you need a piece. You want a piece of scrap paper? You know you love this yellow paper or orangey yellow. It's kind of weird. You want one? Yeah, you're not going to hand this in. We're just going to do it, and you can. But this is just so that you can have something fun. You want a piece too? Sure. Look at this. Yeah. I don't know. There's some of them have A's on them for some reason. I don't know why. But yeah. So I'm not going to collect this. I don't feel like you have to do a great job, but just see if this is for your own sake. Do you remember how to do the Jacobian? Jacobian is equal to whatever. So see if you can do it. Yeah, try to do it yourself. So if you can't remember, then I guess you know. But yeah, should be an individual effort. Interesting. I guess, yeah, so yes, you did it quicker than I did. Yeah, I hadn't checked this one ahead of time. I have the other one done, but that's interesting. So the lesson learned is this is not a good transformation. It wouldn't work. You couldn't use this. Okay, so since you guys know, here, I'll show you my work. 0. It's ridiculous. So yeah, I'm not sure exactly geometrically what this means in terms of these, but apparently what it does is it must take your stuff and collapse it down into whatever. So it's, yeah, this is not a good. You wouldn't want to use this because you get 0 for your. But anyway, if you got 0, you did it right. I just picked 2 functions. I was like, oh, I'll put some u's and v's together. Who cares? You're not going to use it. Oh, I should have done something different maybe. Maybe I should have used, I don't know, if I'd made this just a u here, that would have avoided the problem. Whatever, it doesn't matter. I'll just show you this. Maybe I can bring you, we're not going to do this now because it'll take too long. But I have this on a piece of paper. Maybe I'll bring it next time, give it to you. You can do it as like bonus or whatever. But here's this sort of thing that I thought would be helpful to you, like on an exam, is you have the transformation. So I give that to you, and then here's the integral, and I tell you this stuff, and then I've got a couple of different hints. Yeah, it's like the answer is given to you because the double integral. You remember the story about the guy in 1997 who had the fancy calculator. But anyway, so I have the 2 hints. Transformation could be written like this. So that's this after doing the algebra. And then I even tell you what the Jacobian is, mainly so what I'm thinking is, if I'm giving you an exam, I want to be able to see, do you know how to do the Jacobian? And then, well, even if you don't know how to do it, can you use it? Maybe you blow it when you do the Jacobian, but here I did the Jacobian for you. But maybe I'll give this to you as a little task for next time, but for now, we need to move on. So let me go find my stuff. Give me a sec. It's here somewhere. Not that. That's not what it is. That's for another class. Let's go back. Here we go. Vector calculus. There we go. There, we're moving on. It's so exciting. Vector fields. So some of you are excited because you've already done fluid dynamics. You're like, oh, it's like a happy old friend that you just get to meet again. So we're going to do the basics, just the basics of vector fields. And so that you can understand what it is that we're doing. And then we're going to do calculus. So right now, today, it's just about understanding what a vector field is and sort of dealing with that. And then next time, we'll start doing some calculus in some vector fields. So what is a vector field? Well, a vector field is just a function that assigns a vector to every point in space. So this sort of thing is usually, you've seen this probably before. I've got some pictures here that I can show you that are vector fields. So, here's an example though. So you have this sort of thing. Here, I'll give you a quick example. F of xy is equal to xi plus yj. That is a vector field. So notice that I've taken a point, xy. I could take, let's see. So you could do this for the point. Why is this not writing? Just a minute. There we go. So you could do this for the point 1, 0. The point 1, 0 would correspond with this, I. The point f of 1, 1 would correspond with I plus j. So you know what these look like. For example, the vector I looks like, if I can get this thing to change colors, this vector I is that vector, right? It goes to the right. This vector I plus j, you know what that looks like. It looks like this, over 1 up 1. So every point in space has a vector associated with it. Now you can imagine probably some applications of this. One is the wind field. So here's a couple of wind fields. Sorry about the overlap there. I don't know what happened. But these are just 2. I took these from a textbook so that I didn't have to find my own. But this is San Francisco. If you're curious, there's Golden Gate Bridge would be right here. And so this is the wind on February 20th of 2007. And you can see that you have little arrows pointing in the direction the wind is blowing. And the larger arrows just indicate stronger winds. So if you're on the Golden Gate Bridge, which is right here, the wind is blowing out towards the sea, away from Alcatraz. So Alcatraz here, Golden Gate Bridge, this is the Bay Bridge. So the wind is blowing that way. That's on February 20th. Go to February 21st, notice that the wind has picked up quite a bit along the Golden Gate Bridge, and it's going the other direction, going inward, so in towards the bay rather than out. I think this is typically what it's like in San Francisco. It can be quite windy, but anyway, so you can see each arrow points the direction, and it indicates the amount of the sort of velocity. So here winds are blowing upward and around. Here the winds are kind of swirling. They're not as strong. But that's an example of a vector field. You have a bunch of arrows, or a picture of a vector field. Here's a couple other pictures of vector fields. We have ocean currents here around Nova Scotia. So you have this. So once again, I stole these from a textbook, but they're a good example. So you can see stronger ocean currents are larger vectors. So there's strong currents here and here. Looks like things are pretty stationary here and here. And then you have something going on up here. But anyway, you can see where the ocean, where the flow is. And then here, this is something you might, the fluid, did you do this in fluid dynamics? What's that? Oh, you haven't taken fluid dynamics? Okay. Because this would be an airfoil. I know it's air. You think it's not, well, it's a fluid of sorts. You know, you have wind and air moving across the airfoil or the wind. Although air is compressible, fluids are not. Now, I don't know the difference. But you would, if you're doing fluids, motion of fluids, you'd have a similar situation. So you have the arrows pointing the direction of the motion of the air as it goes across this wing. So you can imagine why this would be important to engineers and other people, and climate scientists are interested in this stuff too. So a force field. Force field is another type of vector field, and it associates a force vector with each point in a region. You could think of like a magnetic fields or the force field. So gravity is a good example of a force field. So here, let's see, we have the surface of the Earth. Here we go. Okay, that's terrible. But anyway, so gravity, that's a good example. So you have these arrows, and those arrows get smaller as you go out into space. So the amount of the force of gravity decreases by the square of the distance. Is that right? But anyway, so the further you go, the smaller the force. Also, where you are on Earth. If you're standing atop Mount Chimborazo in South America, then the force is actually a little bit greater than it is here in Ohio, because there's more mass underneath you, underneath Mount Chimborazo between you and the center of the Earth, whereas here we have less mass between us and the center of the Earth. So there's a slight difference in the gravity, not much. It would be like 9.8 meters per second squared would be the acceleration due to gravity here, and maybe 9.81 down in South America on Mount Chimborazo. But there's slight variation. So, but you have a vector field, so that's a force field. You could also think of magnetic fields. You've probably seen these things. So you have this bar magnet, north and south, and then you have all of these like the iron filings you've probably seen from some physics teacher taking a magnet, putting it underneath a piece of plastic and throwing iron filings on it. You get this nice, beautiful sort of direction field. So the vector field. So we're going to use, just to clarify a couple of things, the domain is always going to be a set of points usually in R2. That's the reals, the real plane, so XY. But it could be R3, which is XYZ. So three-dimensional or two-dimensional set of data points. So you've got these points. We're going to pretty much stick to R2 though. And then the range is going to be a set of vectors. and the vectors we'll call v2 or v3 if you have vectors with 3 components. So let's see, we need some examples. Let's do this. That's boring. Let's see. Well, I'll show you this. It's boring, but we'll do it anyway. So when we do a vector field, when we draw a vector field or sketch a vector field, basically what we do is we sample. We're not going to draw a vector at every point, but we're going to sample, take a sample of points in the plane and apply our function to those points, and then draw a little arrow emanating from those points. So for example, here, this is just a generic example. We'll draw some actual vector fields here in a minute, but you have each of these points, and you'll notice that they each have a vector pointing away from them. So let's actually try. Let's see, I've got one here somewhere. Is this one good? Is this one good? No, that's no good. Just a sec. Here we go, this one. That's a good one. So let's try this. Let's try to draw this vector field. So first things first, we're going to draw our axes and then decide on where the points are going to be. So let's go like this. Let's go out 2 units in each direction. And then this will be -1, -2. And this is 1 and 2. So essentially, I'm going to make a mesh of apparently 25 points. So there's 25 points here. So you can see each of these dots represents a point that I'd like to sample and come up with the vector that goes to this vector field. If I had arranged this better, I could have divided you guys up into, like, given each of you one, because we have approximately 25 people. But yeah, I should have, yeah, there's 4. Yeah, this is a grid. This is a 4x3 grid right here, if you think of this. Yeah, well, that's okay. I'm really not interested in doing this by hand. Gotta be honest with you. I'm only gonna do it by hand once, so, well, yeah, pretty much. So then we'll use a computer. But yeah, let's take a look at what this would be. So essentially what I'm going to do is I'm going to take each of these points, for example, the point 1, 0, 1, 0, and I'm going to plug it into this function. I'll also do this for the point, let's do 2, 1. So I don't want to do all of these. It gets a little bit tedious. Let's do -1, 1, -2, whoops, f of -2, 1, f of 0, 2, just to get a few, get a sampling of what some of these might look like. Okay, so for f of 1, 0, if I plug 1 in for x, 0 in for y, I get the following vector, 0i plus j. So 0i plus j, and that corresponds with this vector. Starting at the point 1, 0, I'll draw the vector. It's 1 unit long. It goes straight up. So it looks so good? Yeah.
Is it not 1i plus 0j?
X is 1, y is 0. So I'm going to plug here. So here, this one. So you have x equals 1, y equals 0 for that point. So y equals 0, x equals 1. Yeah. So it's confusing because we're using this function. So you have 2 things. You have the point xy, and then you have the function that gives you a vector. And we do think of the vector as having an x and a y component. And so yeah, we have to sort of step back and say, okay, let's plug those in here to figure out what the 2 components are for this vector. So thanks for asking that, because I'm sure that if you had trouble, there's 7 other people who are thinking the same thing. Yeah, let's see. So why don't you go ahead and try to do these 4, and then maybe we could randomize this. That'll be fun. Submit my attendant. That's good to remember to do. All right, you might not be done with all 4 of those, but you probably did the first one. So Rachel J, did you do that first one? Or the f of 2, 1? Okay, plus 2j. So let's see, we're starting at the point 2, 1, which is right there. And I'm going to go back 1 and up 2. So that vector looks something like that. Well, this is going to get really ugly really quickly. So we're going to have to try to find a way to make this better. We'll talk about this in a minute. But let's just get these other 3. Cooper C, did you get f of negative 1, 1?
Negative I, negative j.
All right, negative I, negative j. So let's see, negative 1, 1. I'm going back and down. Okay, that one I can draw. There. Looks like that. Is that right? Okay, so let's see. What about Caden? Can you do f of negative 2 and 1?
Yeah, that'll be negative 1, negative 2.
Okay, so negative I, negative 2j. So let's see, that's minus 2 up 1. We're starting here. And I need to go back 1 and down 2. So it's going to look something like this big long vector. That look okay? I guess it's the best we're going to get. Nolan, what about this last one, f of 0, 2?
Negative 2i plus 0j.
Okay, so just negative 2i plus 0j. So let's see, 0, 2. It's negative 2i. So that vector looks like this. It goes clear back to there. So you're starting at this point 0, 2, going back. Wow. Now, if I were to put in all of the vectors, so I happen to know what these vectors are going to look like. This is what you'd end up with, is something that looks sort of like this, where the vectors end up overlapping quite a bit. So this goes like this. This one goes clear over to there. This one's going way down here. This goes like this. Like I said, I've done this before. So if you're like, how are you doing it so quickly? It's because I've done it before. So this goes up here. This thing, where does this one go? Oh, this one goes over. This one, okay. This f of, here, let me do this one though. This one's a good one. F of 2, 2 is negative 2i plus 2j. Check this out. This goes like this. So you have all of these vectors that are overlapping, competing for your, like, how can I, it's hard to see what's going on. And so what typically happens when we're trying to represent a vector field is we have a computer to do it, for one. And then secondly, we tell the computer to take this ugly vector field and let's shrink everything down so that the longest a vector can be is like 1 unit, so that it all gets shrunk down so that you don't have these overlapping things, because it's really confusing to see all of these things overlapping. So let's shrink everything down so that proportionately this vector is, well, this vector here will be twice the size of this vector, but if I shrink everything down, I can still keep that, retain that idea without having the vectors overlapping and be confusing. So here's what a computer would give me, is something like this for that same vector field. Notice that, for one, the mesh is much more fine. It's got many more vectors. It can do it quickly. And then also, they don't overlap. So you can see what's going on. You can sort of feel what's happening. If you can imagine that this is a pond, or this is the surface of water here, is that if you're right here, you're nearly stationary. You're moving very slowly in a circle. Out here, you're moving much quicker, but you're also moving in a circle. So you can kind of see what's happening. There's this flow around this vector field, around this thing. Maybe this is a tornado, and this is, I don't know, the eye of a hurricane, whatever. But this gives you a feel for what's going on. I have on our webpage, let me show you this. You may have already played with this, which is great if you have. If not, let me point you to it once I pull this up and put it up on the screen. Let's see, pull this over. It's logging in. I have the KC Cougar, and there it is. Okay, so if you go down to the bottom, where is it? here it is. So you got CalcPlot 3D and the vector field. So click on this vector fields thing. You don't have to do this right now, but I just want to make you aware of this, that we have this thing that we can use, and it gives you nice pictures of vector fields. They're so nice that I use them when I make quizzes and tests. I just have this do it, and I get a screenshot. But let's see, add a vector field. Let's see, it's been a while since I've done this. Let me do it up on, let me see. Okay, so, well, let's get this vector field. Here we go. So we had negative y times I plus x times j. Is that, yeah, there it is. Isn't that beautiful? So very nice. You have this nice sort of flow, a nice mesh. There's probably some other things that we could adjust on this. You know, you can change the settings here. I haven't played around with this much. I'm just excited that we can easily come up with a vector field. So that is available to you. You can click on that link to help you with your homework if you need it. Okay, so what we're going to be interested in, at least for today, is distinguishing between different vector fields, just getting a general feel for a vector field. Let's see, do I? No, okay, we'll deal with that in a minute. So for example, you can see that these are definitely not the same vector field. And so understanding, you know, being able to distinguish one from the other, and I honestly can't remember what the functions are for these, but I do have some that I made that we can do. This is kind of like your homework where you're trying to distinguish between different vector fields. And I know it looks scary. You're going to be like, oh, do we have to do this again? Yes, we do. So like with the vector functions, remember drawing those curves or the surfaces. So this just helps you to be able to distinguish or to understand what's going on with the vector field without having to draw the vector field yourself. So let's take a look at these 5 and see if we can distinguish between them all. And what I would suggest you do if you have a problem like this, which you will on the next quiz, will be basically this, is to, first of all, stick with the things that are simple. So what I mean by simple is you'll notice that this first vector field, number 1 is very simple. It's just j. That's constant. What that means is that no matter where you are in the plane, wherever you are, you're always doing the same thing. F of xy is j, meaning, I guess, you're pointing upward, right? So no matter what x and y are, you're going to just go up. So this is up, up, up. This one. So that's number 1. So see if you can match up the others. Just, you know, take a minute. So this one is number 1. Don't match that with any of the others. But see if you can match up the other 4, just for fun. And then we'll talk about the differences and how you might distinguish one from the other. So some of them are going to be obvious and some not so. And I need to check something. Here we are. Okay. Oh, come on. Okay. All right. I just wanted to pull up the homework so that, because I don't have my book with me, make sure I understand what we need to do. Okay. So let's see how we did. Oh, get my randomizer out again, right? So y'all want to do it. Here it is. Okay. So who gets to be randomly chosen? Joshua, what do you think about this next one? F of xy is equal to xi plus yj.
Would be the top right.
Top right. That feels pretty good to me, doesn't it? So I'm going to put a 2 here with a little question mark. Because it looks pretty good, right? Because xi plus yj, it feels like things are moving out. So for example, if you put the point 1, 1 into that, you're going to, so the point 1, 1 is up here. You're going to be going over 1, up 1. So that's this direction. If you put the point 1, negative 1 into this, you go over 1, down 1. So it's like an explosion. Very nice. All right, let's get the next one. What about number 3? So Rachel P., what do you think of number 3? What would you like to, where would you like to put that? On the bottom? Yeah, that sounds good to me too. So that one feels good because here you'll notice that I is constant. So you're always going to the right. So notice that the I is constant. So that means that every one of the vectors on this vector field should be pointing that way. But the difference as you move across is the, wait, where are we? Oh, there it is xj. So when you're over here, you have a negative number for x, and so I should be pointing over but up. And then as I go closer to the origin, the angle goes down and you're just pointing straight across. And then as I move further over, you're now pointing down, down, and then when it's very steep. So this one, especially on the ends, it kind of feels like it's straight up and down, but it's not. So you're going upward but over to the right, and then as you get over, you have the same phenomenon on this line where x equals 0. You're just pointing straight across, and then you start going down. Very nice. Okay, let's do this next one. Oh, let's do the last one, number 5. 5 is a good, relatively easy, I think. But who gets to do 5? So Luke, what do you think about number 5? Yeah, the far left is number 5. You see that cosine, you're like, well, the only thing that goes up and down is this one here. There. But let's just check. Let's just see what if we can understand. You have negative I. So notice that's a constant as well. Negative I is that way. So I'm pointing that way. The only thing that changes is as I move, as x changes, you'll be going up or down, up or down. So that's exactly what happens here. You have this up, down thing going on. Okay, so the last one is this number 4. And number 4 and number 3 are surprisingly similar. That's why I put that, or no, not number 3, number 2. Sorry about that. Number 4 and number 2 are very, very similar. Oh, come on. I'm just trying to erase and it wants to advance or whatever. Okay, so number 4 and 2, that's why I put the question mark there, because here, is this 4 or is that one? So notice that the big difference, so if you were to put numbers into this, you would get a similar situation where everything is moving away from the center. So how do I distinguish between 4 and 2 is the big question. Well, you'll notice that the difference is that with number 4, you're dividing by basically the magnitude. So number 4 is like number 2, only you've divided by the magnitude of that vector. So this one actually is a unit vector. So here, all the vectors are unit vectors, whereas this one up here, the vectors are smaller when you're closer to the origin and bigger as you get further from the origin. So whoever it was, you'd be forgiven for thinking that that was number 2. That's why it's like, you know, it's a good choice. But in fact, that's number 4, and number 2 is this one down here. So the correct answers are, this is number 4 because all the vectors are the same length. This one is number 2 because the smaller x and y are, the smaller. So you could even do this, like take a, let's just take to compare. Let's compare these for number 2 and number 4. If I did, oh, it's almost time. I see you're packing up. Okay, if I did this, let's do f of 5, 0, f of 5, 0. So with number 2, f of 5, 0 is 5i. For number 4, f of 5, 0 is just I. So here, 5i, your arrows are getting bigger and bigger as you go along the x-axis. Here they stay the same length. They're all 1 unit long. All right, well, I don't know. I haven't had a chance to peek at the homework, but hopefully I picked problems that are going to be easy enough for you. But if you see anything weird, just read the book. You can do that. I know you can.